All right, everyone, in this lesson, we are going to explore the relationships with 30, 60, 90 triangles. So this 30, 60, 90 triangles, they are a second type of special right triangle. And our 30, 60, 90 triangles, they actually come from an equilateral triangle. So if you think about an equilateral triangle is a triangle where all of the sides are the same lengths. Okay, so all the sides are congruent. So I'm going to mark them with the same tick marks. And if I think about the fact that all of the sides are the same, or all the sides are congruent, then I know that all of the angles must be congruent as well. And when I think about what those angle measures could be, if all the angles have to be congruent, there's 180 degrees in a triangle, that tells me that every single angle has to be 60 degrees. So then you might be wondering, well, where does that 30, 60, 90 part come from if all the angles are 60? Well, what we're going to do is we're going to take an equilateral triangle and we're going to cut it straight down the middle, and we're going to draw the height in. And when we do this, we're going to essentially ignore one of the sides. So I'm going to cross off this left side. And so now when I drew the height in, this is kind of a messy triangle. When I drew that height in, that height is perpendicular or forms a 90-degree angle with the base. So now I have a 60-degree angle and I have a 90-degree angle, and that third angle I can think of triangle sum. So if I do 180 minus 90 minus 60, I get that this angle here is now 30 degrees. Or I also could have thought of it, if I'm drawing the height in, which is going straight down the middle, then I would cut 60 in half to get 30 on both sides. Well, since I'm only focused on one side, I'm just going to mark 30 there. So that is where our 30, 60, 90 triangles come from. So what we're going to do is we're going to do a little exploration, very similar to what we did with 45, 45, 90 triangles, except we are going to use what we call isometric dot paper instead of graph paper for this. So what we're going to do is we're going to create 3 different equilateral triangles with lengths of 2, 4, and 6. So I'm going to start with the length of 6. So with isometric dot paper, horizontally, the dots are the same distance apart, and diagonally, the dots are the same distance apart, but vertically, the dots are not the same distance apart as it is diagonally or horizontally. So that means when we use isometric dot paper, we can only count the distance if our lines are horizontal or diagonal. So I'm going to draw a length of 6 in. And I'm going to label all of these sides as being 6. And because this is equilateral, I know that all of my angles are 60 degrees. Now, I'm not going to mark that top one. You'll see why in a second. But since we're going to explore 30, 60, 90 triangles, we are going to draw our height in. And when we draw our height in, we're going to ignore one whole side. So we can either cross it off or you can erase it if you're writing with a pencil. And so now when I draw the height in, this is now a 90-degree angle. And when I look at the side of the bottom, I can see that my side length is now 3. And then this is where my 30-degree angle is. So the question that you're going to ask yourself is, what is the length of the height? So if we look at the information we have, we can see that our short side is a length of 3. And our hypotenuse is a length of 6. And we don't know what the long side is. So I want to make sure you guys understand, hypotenuse is very different from the long side. When I talk about the long side, what I'm really talking about is the longer leg of the right triangle. So if I think, what do I have available to me that allows me to find the missing side of a right triangle? Hopefully Pythagorean theorem crossed your mind, and I can use the Pythagorean theorem. And I have to be careful here because I'm solving for a leg, which means I'm solving for either A or B. So I'm going to choose to solve for B. So then that would be my equation. And if I start to solve this, I need to square 3 squared and 6 squared and actually calculate that. And then I'd have to subtract 9 from both sides. Forgot my b squared there. B squared is 27. And then to undo a square, I have to take the square root. and I get b equals the square root of 27. And so you might be thinking, oh, I'll just leave it there. But my directions, the 4 steps says simplify the answer so it remains in radical form. So if I think about how to simplify the square root of 27, I'm a fan of the perfect square method. So the biggest square that goes into 27 is going to be 9. So I could do square root of 9 times square root of 3. Square root of 9 is just 3. So that means the length of that longer leg is 3 root 3. So what you're going to do is you are going to do this exploration on your own for triangle 2 and triangle 3. And so for triangle 2, I want you to do a length of 4. So I'm going to go ahead and draw that in. So you're going to do the same process that we did with that maroon triangle in example 1. And then for triangle 3, you're going to do a length of 2. Okay, so you're going to pause the video and you are going to do this on your own, and just know when you unpause the video, I'm going to have already worked out triangle 2 and triangle 3 for the side lengths, and so you'll want to compare your answers to mine. And then when you finish doing your exploration, I then want you to see, what do you notice about the side lengths in these trials? Like, how can you use each side length to find another side length? Okay, so like, what are the patterns that you're noticing? So go ahead and pause the video, complete triangle 2, triangle 3, and then what do you notice? All right, so you should have worked through triangle 2 and triangle 3, so you can see my work here. I'm going to give you a couple seconds to look that over and see if you came up with the same lengths that I did. So let's talk about what you notice. So I'm going to zoom out a little bit so we can kind of see all of our information. So let's take a look, and one thing we should notice, or something that came to my mind right away, is every time I drew my height in and I relabeled my right side of the bottom of the triangle, I noticed that it was half of the hypotenuse. And so if you look at our short sides, so I'm going to mark these here. If you look at our short sides compared to the hypotenuse, hopefully something that came to your mind is that the short side is either half of the hypotenuse, or you can double the short side to get the hypotenuse. So one relationship that exists is if we want to know what the hypotenuse is, we take the short side times 2. Or we can think of it as the short side equals 1/2 times the hypotenuse. So let's take a look at that longer side. So you may have noticed that the longer side, every single one of them has a square root of 3. And then I don't know if you noticed this, but if you look at the number in front of that square root 3, what does the number in front of the square root 3, where else do you see that with your links? And hopefully you're recognizing that the number in front of each square root of 3, and on this triangle 3, you could technically draw a 1 in if that helps you. So you notice that the number in front of the square root of 3 is actually the short side's length. So if I want to find the longer leg, or the longer side, I'm going to do the short side times the square root of 3. So those are the patterns associated with 30, 60, 90 triangles. And in the next video, we're going to do some actual solving and applying this pattern that we see.